Hello, my name is Randall Irwin. I'm a PhD student in the Department of Electrical and Computer Engineering at the University of California, Los Angeles. I work in the Center for Heterogeneous Integration and Performance Scaling, or CHIPS, under Professor Subramani and Iyer. Today, I'll be discussing my work on flexible connectors and PCB segmentation for signaling and power delivery in wafer-scale systems. So here's an outline of my talk. First, I will introduce and motivate my work. Next, I'll discuss our progress on the two projects, which are the focus of this talk, FlexCon and the Compliant Power Platform. Finally, I will conclude my presentation and discuss what we have planned for our future work. So moving on to the introduction. Bandwidth requirements have been steadily increasing over time, which we see as an example in the figure to the right for peak memory bandwidth for CPUs and GPUs since 2008. Example applications which are currently driving this trend are high-performance computers, artificial intelligence and machine learning, and systems on wafer. For the Silicon Interconnect Fabric, or SIIF, which is a system on wafer enabling heterogeneous integration developed at UCLA Chips, we have demonstrated a die-to-die bandwidth of more than 2 terabits per second per millimeter of die edge length. Continued scaling of systems on wafer, such as the SIIF, implies the usage of multiple wafers in addition to off-wafer communication to, for example, a PCB. Meeting bandwidth requirements for wafer-to-wafer or wafer-to-PCB applications necessitates the development of novel, flexible interconnect technologies. Given such a technology could be integrated with a silicon wafer, this also suggests it can be used for chip-to-chip communication. Existing commercially available flexible connectors include the Amphenol ICC high-speed flexible printed circuit connector, which has a bandwidth of 33.33 gigabits per second per millimeter, the Samtec Direct Connect chip package cable with a bandwidth of 50 gigabits per second per millimeter, and the Molex high-speed flexible printed circuit cable with a bandwidth of 70 gigabits per second per millimeter. I would like to note here that these bandwidths are normalized to the cable width and do not factor in the width of the connector. Furthermore, the connectors for these cables are designed for connection to PCBs or packaged chips and are therefore incompatible with direct connection to a wafer. For such a cable to be used in a system on wafer, the connector must be compatible with assembly to a silicon wafer or a similar substrate. To meet these requirements, we propose FlexCon, which is a flexible, high-speed, high-bandwidth connector cable for I/O delivery. Channels on FlexCon operate at 32 gigahertz and provide an overall bandwidth of 240 gigabits per second per millimeter, which is more than 3x the Molex connector, and to our knowledge, the highest bandwidth for flexible connectors to date. FlexCon is connected via solder connections, and this enables wafer integration in addition to conventional PCB integration. Additionally, in eliminating the bulky plastic connectors used in the commercial cables allows us to greatly reduce the area required for connection. Next, for a system on wafer, delivering power to the periphery of a wafer results in I²R power losses and voltage droop, as depicted in the figure to the right. Cooling a system on wafer requires the usage of the full area of one side of the wafer, typically the die side. For further information on cooling wafer-scale systems, I would like to direct the viewer to a talk given by my colleague Josh Shaw, which was given at this year's iTherm conference. So therefore, power must be delivered through the wafer backside using through-wafer vias as depicted in the figure to the right. However, as we understand that in conventional packaging, as die size increases, the thermal stresses also increase, which results in assembly warpage. So given that a system on a wafer is essentially a very large die, we would expect very high thermal stresses in such an assembly. Mitigating these thermal stresses can be achieved by reducing the effective size of the substrate and PCB assembly. So to achieve this, we propose the Compliant Power Platform. In this approach, the PCB used for power delivery is divided into smaller segments embedded in a flexible PDMS substrate and electrically interconnected. Each PCB segment is bonded to the wafer via solder BGAs. Power is delivered from power boards on a separate power delivery assembly to the segment backsides via flexible cables. Additional area on the segment backsides can be used for decoupling capacitors. For additional information on the architecture developed for power delivery in the SIIF assembly, I would like to direct the viewer to a talk, which is talk 5 in session 4, which is given by my colleague Kanan. Next, I will discuss FlexCon in greater detail. So to analyze the performance of FlexCon, electrical simulations were conducted using ANSYS High Frequency Structure Simulator, or HFSS, which is a full wave simulation software. The simulator geometry is shown in the figure at the bottom. Each channel consists of differential microstrips with 20 micron line in space, and the pitch of the channels is 133.3 microns. FlexCon was designed to operate at 32 gigahertz to achieve a bandwidth of 240 gigabits per second per millimeter. The top left figure shows the insertion loss of a channel with a length of 20 millimeters up to 32 gigahertz. And we see here that the insertion loss is less than 6 dB. Near end and far end crosstalk results are in the top right figure, where we see less than 30 dB for both at 32 gigahertz. To analyze the signal integrity of FlexCon, 3 separate simulations were conducted in HFSS, which are the microstrip channels, which I've just shown, the solder connection from the FlexCon to a PCB, and the solder connection from the FlexCon to a silicon wafer. The results from these simulations were exported into equivalent circuit elements in ANSYS Circuit, which is a SPICE-based simulation software. The block diagram in the top right shows the circuit analyzed here, and parameters are shown in the table at the bottom left. The resulting eye diagram is shown in the bottom right, where we observe excellent signal integrity. Given the results of these simulations, we expect to be able to achieve a more than 100 terabit per second aggregate I/O bandwidth for a 300 millimeter wafer. So to validate the results of these simulations, test sites consisting of GSSG wiring at 40 micron pitch were fabricated. RF measurements were performed using a Keysight PNAX virtual network analyzer and Cascade Microtech Infinity probes. The test sites were modeled in ANSYS HFSS as fabricated for comparison. We observed that the measured insertion loss compares reasonably well with the results of the simulation, suggesting our previous simulations are valid. The process for fabricating FlexCon is an adaptation of the FlexStraight process, which is a fan-out wafer level packaging process developed at UCLA Chips for flexible electronic packaging. First, we place dies on a handling wafer laminated with a thermally releasable adhesive. The purpose of these dies is to provide structural support beneath the bonding pads and ensure planarity. The PDMS molding compound is then dispensed onto the handler and compression molded between the first handler and a second handler, which has been laminated with a thermal tape with a higher release temperature than the first. The first handler is thermally released, and a stress buffer layer consisting of parylene C and SU weight is deposited. SU weight corrugations are then patterned, which we have previously demonstrated enables interconnect flexibility. A seed layer of titanium and copper is deposited and thickened via electrodeposition. An SU weight dielectric layer is deposited. Vias are patterned, followed by corrugations. The ground vias are filled via electrodeposition. Interconnects are formed using a semi-additive plating process, and finally the wires are passivated with parylene C and solder is deposited onto the pads. Next, I will discuss the compliant power platform. So as I mentioned earlier, the thermal stresses are present in organic substrate to die assemblies. And this is a direct result of the mismatch in coefficients of thermal expansion between the different materials that make up the assembly. For a given change in temperature, the difference in thermal strain between two materials is given by the product of the CTE mismatch, the temperature change, and the length of the assembly. By reducing the effective length, we can reduce the thermal strain difference, and this can be achieved by dividing the organic substrate or PCB into smaller segments. So here we consider a square PCB with an edge length of 300 millimeters bonded to a silicon wafer of equivalent dimensions. If we evenly divide the PCB into n by n segments and assume each segment is placed as closely as possible to one another, which is dictated by the thermal expansion of each segment, the maximum relative displacement between the PCB segments and the silicon wafer is given by the equation here, which is plotted in the figure to the right as a function of n. CTE mismatch induces warpage of the assembly, which is given by the formula shown on the left, where T is the assembly thickness and D is the effective flexural rigidity. The remaining parameters are dependent on the material properties and assembly geometry, and details of this analysis can be found in the paper cited at the bottom. So here we assume the assembly consists of a silicon die or wafer, which has been perfectly bonded to a PCB. The assembly experiences an isothermal change in temperature and undergoes spherical bending. Material properties are assumed to be linear and isotropic. A cross-section of the assembly and the material properties used in the study are shown in the bottom right. Results of the theoretical analysis were compared to simulation performed in ANSYS Mechanical for 2 different PCB thicknesses and assembly lengths, and we observed very close agreement. The effect of dividing the 300 millimeter PCB into 30 millimeter by 30 millimeter segments resulted in a 27% reduction in warpage for a PCB thickness of 1.6 millimeters. However, since we're assuming the materials are linear and isotropic, this analysis does not capture effects such as the orthotropic and anisotropic nature of silicon and the PCB and any nonlinear effects. We also assume that the effect of PDMS is negligible because of the very low Young's modulus. So similar to FlexCon, the process flow for the compliant power platform is an adaptation of the FlexRate process flow. We first place the PCB segments onto the first handler. Next, PDMS is dispensed and compression molded. The first handler is thermally released, followed by deposition of the parylene C and SU8 stress buffer layer and SU8 corrugation formation. The wiring level is formed via a semi-additive plating process, which is then passivated with parylene C, followed by etching to the BGA pads on the PCB segments and solder ball deposition. The compliant power platform is then bonded to the silicon interconnect fabric, and the second handler is thermally released. The PDMS backside is patterned via laser etching, after which the PCBs are populated with decoupling capacitors. And at this point, the power platform is ready for assembly to the power boards. So finally, to conclude this talk, FlexCon is a high bandwidth flexible I/O connector enabling wafer-to-wafer, wafer-to-PCB, and chip-to-chip communication. An aggregate I/O bandwidth of more than 100 terabits per second can be achieved with a FlexCon on a 300 millimeter wafer. Bonding with solder enables integration with wafers, chips, and PCBs or laminates. The compliant power platform mitigates thermal stress-induced warpage caused by CTE mismatch between silicon and organic substrates such as PCBs and laminates. This enables backside power delivery in wafer-scale systems, but this approach can be easily extended to, for example, large-size dies on a laminate. Our current and future work for FlexCon includes increasing its length without impacting performance by replacing SU8 with a low-loss dielectric such as polystyrene and embedding active components such as signal buffers and linear redrivers. We are currently working on optimization of the bonding process. Initial development of this process has been promising, and to the right we show one early result in which a FlexCon was bonded to pads on a silicon test vehicle. RF measurements of bonded FlexCon samples and reliability study of the bonded samples, including temperature and humidity cycling, high temperature storage, and cyclic mechanical bending are also in progress. For the compliant power platform, we are working towards demonstration of a 100 millimeter scale prototype and a reliability study of the prototype. Finally, I would like to thank all of the members of the CHIPS Consortium for supporting this work. And if you are interested in the work we do here at CHIPS, I would like to invite you to view the talks from my colleagues given at this year's ECTC conference, which are listed here. Thank you.